exciting. Okay, so I'm gonna continue. So we finished last time. This is the fourth one, okay? I open the full, you can open the no solution one. And I'm gonna continue after what we saw last time. We stopped and think about these things. By the way, just at the beginning, be sure that you are calling these libraries, okay? And we don't need anything else. Then you can go to directed graph, and this is what we are going to be doing today. It's very similar to what we did last time, but now with a directed graph instead of a non-directed. And also another difference is like the network we're going to create now is coming from a data frame. Last time we did it from a matrix. And usually what you will be doing is creating it from a data frame. So this is what you will be doing. First, we have to set the working directory. And then we are going to load the data. This is the same data we've been working with so far. This is the nodes data frame. I always load the data and I have a look at it to remember what I'm working with, but also to check a little bit if it was loaded correctly, if it has the dimensions that I expected, if I have some NAs or not. So the typical thing that we've been doing so far. I'm also loading the edges data frame, and I do the same thing. You can run this code and have a look at it. Okay. Then, well, as always, my code is a little bit my input, but a lot of it is coming from somewhere else. As I say many times, we have the references at the end of each PowerPoint slide, and sometimes I will also put them here. This Cateto website is amazing for network in iGraph, and there are also some more. This is another good website. So what we are going to start doing is something that we already did yesterday, but I didn't explain. I said I will explain it today more. So we're going to be creating a new graph that is called GD, Graph Directed. You can call it however you want, but for this workshop, please call it the same. And we're using this function, create a graph from a data frame, okay? For this function, we're going to need a data frame of edges, okay? Ours is called edges, but it could be called something else. So that's when we do d equals, so this argument is going to be our edges data frame. And then we have vertices, which is a synonym for nodes, and the vertices equal, it's this second argument, and it's going to be equal to our node data frame. These two data frames, this is something I talked about another day, but I want to repeat it because just listening to things once doesn't mean that you learn them or remember them. So edges data frame needs to be a data frame with at least two columns. The first one, if it's a directed network, the first one is going to be the origin of your edge, and the second column is going to be the destination of your edge. Okay, so every edge data frame has to start like that. Then you can have or you cannot have, or you might or might not have edges attributes. But those two first columns are very important, and they have to be placed at like the first two columns. For the vertices, we need for sure one column that is going to be the specific node ID. And then you can have node attributes if you want, or you might not have them if you don't have them. This node ID has to be unique for each node. So for example, if we are talking about people, if you just write down the name, like John, that probably is not going to be a unique identifier, because if you're talking, I don't know, about the people within a building, most likely you're going to have two Johns. So maybe it will be a good idea to say John and last name, or John, last name, and the initials of the department this person's working in. Something like that that can be a unique identifier.
So can it be a character or a number?
Yeah, so can it be a character or number? It can be whatever you want. Mm-hmm. Yeah.
So you're saying, so if you had a file and of just transfers of facility A and facility B, you can only do this if there's a unique row for A to B or A to G, A to whatever. Like you can't have multiple A to Gs.
No. So what you're talking about is the node table, because you're talking about a link, no?
Yeah.
So the link can be repeated.
It can be.
Yeah, and actually, if you have more than one transaction from A to B, you should have more than one row that start with A and finishes in B. Because in the edges data frame, each row is a transaction. Each row is a different link. Okay? But you can have the same origin and the same destination. For example, if an edge is a conversation during one day, I might go to you and have a conversation with you maybe at 10, and then I have a question, and then I go to you again at 11, and then I go to you again at 5 p.m. Okay, so that will be recorded as 3 different rows of Esther going to Sam, and then an edge attribute would be time. So Esther goes to Sam at 10, Esther goes to Sam at 11, and Esther goes to Sam at 5. So those will be 3. But the unique identifier is my name, Esther. Because there might be more Esthers here, it will be better if either my unique identifier will be my social security number, or it could be
CMS provider number, something like that.
CMS provider number, as
So
long
it can
as...
be repeated as long, but it has to identify a single person.
Exactly. It can be repeated in the edge file.
In the edge file.
In the node file, it cannot be repeated.
Wow.
And actually, yeah, if you repeat it in the edge file, if in the edge file we have 2 Esthers, it's going to tell you, hey, there are duplicates in this file and you cannot have duplicates. Okay? And that's how you find out that in your node attribute you don't have unique identifiers. Well, because it's going to tell you, hey, no, there's something bad here. Okay? And that's why I was emphasizing the importance of this unique identifier, because if you have a node, like 2 different nodes with the same name, then you cannot do any of this. You cannot do an in degree, you cannot do an out degree, because you need that unique identifier to know how many transfers that unique person or facility is sending or receiving. Okay? So in the nodes data frame, the unique identifier cannot be repeated in different rows, but in the edge data frame, it can be repeated in different rows. But that unique identifier is unique to a specific facility or a specific person, whatever our node is. Okay?
And what if you have a patient, if you're looking at patient and not facility?
So
you have patient A going to, you have patient A, I don't know, maybe you want to look at contacts. If patient A had a contact with patient B, for example,
so
then could you have a repeat of patient A
in
the source, and then...
Yeah, in the edges data frame, you can have a repeat. That's totally fine, but not in the nodes. So when we are talking about nodes, a node could be a facility or could be a person. It depends on which level you're or could be a department.
Yeah, the little
Bubble.
Is the node.
Yeah.
So that's why you're saying cannot have a repeated, because you only need one that will, later have...
It cannot have a repeated value in the nodes table because it's unique. The nodes table is telling you which are the participants of our study, let's say, which are the nodes, and that node table has to be unique. In the edges, because that one node might be interacting with different nodes, and in the edges data frame, each row is a transaction or an edge, you might have that node repeated in different rows, but in the edges table.
Yeah, okay, got it.
Good, perfect. Thank you for the questions. Okay, so we are going to create that graph. We are providing the edges, we are providing the nodes, and we are saying it's a directed network, okay? So I run it, and we see it here, okay? It says it's a list, okay? Well, let's see. Class of GT, it's an iGraph, okay? It's not just a list, it's something a bit more special. It's an iGraph network, okay? There are different packages. Instead of iGraph, we could be using network package or SNA package, But iGraph is the one that is growing a lot, and a lot of people are using it. And yeah, I use iGraph because there are a lot of different functions we can use with an iGraph object.
That's
So
the one I was trying to use.
yeah, I think it's the best. Yeah, yeah. So if we call GD to look what's inside, to look what's there, we get all this. We already saw it last time, but I'm explaining. We have iGraph here, and this is a random number that you will have a different number, okay? And if I run this node again, this graph again, if I create it again, and I look at that number again, it has changed, okay? So every time you create a new one, it's gonna have a different value, so I don't pay a lot of attention to that. But then we have this dn dash dash, okay? That is explained here. D, you could have a D or a U in the first position. These are 4 different positions that indicate something about our network. The first one is going to be either a D or a U, and that will be directed or undirected. The second one is telling you if the network has names for the vertex or not, for the nodes, okay? And ours has a name, which is these ones here. And then 2 dashes, and these are dashes because we don't have anything for that. For the third position here, we would get a dash if we have nothing, or a W if it's a weighted graph, okay? And that means that the edges have a weight attribute. We're going to see this later on. The fourth one here that we have a dash, if we will have something, it will be a B. And a B is a bipartite network, which is something that we are not going to be using here, but for you to know, it's they talk a lot about memberships. Like imagine that we are the nodes, people are the nodes, and we belong to different associations, like I don't know, the American Statistical Association or the epidemiology, whatever. So those associations will be another level of the network, okay? So this will be a network with 2 different levels. Those associations, we could be sharing some of them, and like for example, I could be a member of those 2 associations, but maybe Moniz is member only of one, and Sam will be member of another one. So then we have like a 2-level, like a multi-level network, and that's what a bipartite network is. I never work with them, but yeah, they are interesting when you are thinking of this type of hierarchical association, when you, like the person or the lower level node, can be part of 2 of them. I was thinking maybe we could do something with bipartite networks in hospital and the different counties, but then it's like, no, it's impossible because a hospital it's only in 1 county. A hospital cannot be in 2 different counties at the same time. So I don't know how we will be able to use it. So we will not see this in my workshop.
I'm thinking just if we look at within a region, you might have like corporations of hospitals, like Kaiser,
yeah,
or
yeah,
a patient would only go
yeah,
to that
yeah,
network of hospitals or
yeah,
network of, so you might.
Yeah, so that could be a good idea. If we want to work with this and we want to see that type of relationship, maybe we could work with corporations of hospitals, or maybe, I don't know if the lab thing.
Well, so I don't know if I'm interpreting this correctly, but I mean, certainly we have situations where the nodes have are different types. So there's hospitals versus nursing homes, for instance, and we'd want to display that here.
But
and oftentimes there's more than one level, right? So
the same hospital is 2.
No, it would. Every node would be either a nursing home or a hospital.
Yeah.
So the node doesn't have 2 levels. The node only has 1 level. But I'm just thinking, like, there is a way that we're going to work with where the nodes could be separate. I mean, you have like slaughterhouses versus.
Yeah, exactly.
Yeah.
So what is this thing? When we are talking, let's look at that. If we have nodes, we have this, no? Market, industrial, slaughterhouse, whatever. Well, I have scale or premise type. But yeah, premise type will be market, slaughterhouse, or farm. And this will be, and you can look at that, like summary, nodes, scale. So we have these four.
Yeah.
So for the type of facility, we could do the same. We could have them here. So what is this? What are all these things here in the nodes data frame?
Column headers.
They are column headers, yeah, they're different columns, and these are
For the type of the scale, for the, specifically for the location of that.
This is for the location, and this is explaining different characteristics of each of these nodes. So all these are node attributes, okay? And this attribute is for this node. This attribute is for this node. And what you're talking about, the type of facility, will be a node attribute. So that will be something that we're going to have in the nodes table.
For the I think, so the bipart.
Yeah, I don't know how to pronounce it, but
It's another thing, right?
it will be a bit different, yeah.
Yeah,
Another example that I can give you,
But
yeah.
that Kaiser thing, I think, might.
I think that could work, definitely.
Well, I'm just trying to visualize like how that would look. So it basically like if we had if we say we had like a hospital where we would just want Medicare. So there's Medicare and non-Medicare patients, and so by using this bipartite, we could specify if we just want to look at the Medicare. And it would give us a graph for just the Medicare.
But think about it.
Or-
Being Medicare patient, is it a node attribute or not? Is it an attribute of that patient or not?
Yeah.
It would be an attribute. Yeah, attribute.
Yeah. So then we are in the same thing. That will be a normal network, not bipartite. I will give you another
Trying
example.
to think of what
Yeah, I think the Kaiser example could work. Look at this. So-
okay.
Yeah, let me see. So imagine these are the people, and this is, I'll give you another example, but this is visually, this is what it is, and these are the membership. But this could also be, yeah, imagine, yeah, this could be just classes. This could be students, and these are different classes that students are taking. Some of the classes will be shared by different students. But then this student is, for example, taking this class that this one is not taking. So it will be if you flip this to the left, you'll see this hierarchical kind of structure. And this is what I think the example of Kaiser could work. We'll have to think about it more because I'm not very familiar with how the healthcare works here. But
No one is.
yeah, no one is. But this is the idea, that there will be this bigger, higher level, and the lower level nodes might be sharing some of those higher level, or might be choosing two different ones, and the same lower level could be in two of those. Okay, this is why for me the example of the membership is one of the best examples, because I can see that I can belong to. This person belongs to this association, and this one belongs to that one, but also to this other one.
Yeah, no, I'm looking at another thing on Math Online. Yeah, it makes it pretty clear.
Yeah?
What they mean.
Okay, let's see. With myth.
Yes. Don't censor that.
Only good
Yeah,
results.
Yeah, that first one is.
This one here?
Yeah.
Okay, yeah,
Yeah.
exactly. Okay, this one, yeah. Okay, perfect.
Yeah, one of the annoying things about R, I'm realizing, like, it's nice that you wrote all this out for us, but, like, why do they use D and N and W? Like, why not just say
Yeah.
weighted graph or mean graph
Yeah,
or directed or undirected graph? But
yeah.
anyway,
So yeah, well,
that's just part of.
That's why it scares people, because
Yeah.
you see all this
definitely,
nomenclature and
definitely. But I mean, nowadays, now that I'm creating this material for the workshop, I'm so happy that the documentation has improved, because really when I started, it was, and that was not that long ago, but it was hell.
Same as when I started.
Yeah.
Probably, yeah.
Yeah.
After you
They're
mentioned,
like-
it was not.
Yeah,
very
so many
clear.
things, and with this tidyverse, they also have like tidy graph, for graphs. And then there's this other guy, Thomas, who's creating a gggraph package, which is really good. I mean, it's like, and you have documentation for that, and you can learn what these things means. Of course, you need time, so it's great that I think I'm doing that work of researching, and then I'm giving you like the basics of it, so you save time. But yeah, a few years ago, it was really hard. Okay, so we run the network, and this is what we have. Okay, we were looking at this random thing, these 4 indicators in case you want to see how your network looks like, and then these 2 numbers. The first one is the number of nodes we have. The second one is the number of edges we have, okay, in our network. Then it's saying, okay, you have some attributes, and you have the name attribute that it's a vertex attribute, and this is one of those attributes that it's basically created on its own. And then, well, this C here, it explains that it's a character attribute, okay? That's something I never look at this one. I only want to know, but I mean, you can. The information is there. I want to know if it's a vertex or an edge attribute. And right now, if you compare it with what we had yesterday with the undirected network, I think we only had like name as vertex attribute, and then we added color and gender as vertex attribute. But here, we already start with a large bunch of vertex attributes, and that's because when we said take the table or the table nodes as your nodes argument here, the table nodes already has all these variables, so these are going to become vertex attribute in the network, and that's what we see here. Okay, all of these have the V that shows that it's a vertex attribute. Same or similar thing happened with edges. If you call edges, you're gonna see that these are the columns of the edges table that we use to create the network. Okay, so that's what you see when you call an iGraph network. Okay, and these are as it's explaining, vertex names. And if you see this here, this already it's telling you that it's a directed network. If you remember the non-directed one, I'm gonna run it quickly so you can. This is GU. It's a graph undirected. That's the name I gave it. And you can see we only had the vertex attribute at the beginning, and the edges, the links between the nodes, were depicted by 2 dashes because this is undirected.
So we don't know who is sent.
We don't know exactly. Okay. This is just, there's a relationship between them, but we don't know who's the one who is initiating that relationship or who is sending if we are sending. However, this one here, we know that Brandon sent to Anissa, okay? And this will be like a specific CMS for a healthcare facility to another specific CMS, okay? Is that clear? In this example here, this is a loop, okay? Remember the loops I talked about yesterday? This means that this facility sent to itself a patient, so maybe they just transfer it from one department to another. Although, well, this is a farm data frame, so this is like the pigs from this farm were sent to somewhere else within the farm. Okay, so that will be a loop, and this is something that you need to decide if it's important for you. You think about the epidemiological consequences of including the loops in your analysis or excluding them. I usually exclude them. But it depends on what you are trying to do. Is that clear? Okay, so I'm going to go back to the direct graph. We were here, we just ran the iGraph, we looked at it. And now we're going to start the simple visualization that we did last time. I'm setting the seed again, so you have the same output as I have. And then I just plot the network. And this is what I get. So it's really messy, I cannot see anything, so I definitely want to change it. Okay, so to improve it, I'm going to start adding different arguments to this plot function, okay? So I say plot, and you can also say plot.igraph, but the shortest the better, because we want a clean, short code. We call the name of our network, and then I'm going to start tuning it. I have the vertex size, I said, okay, give it a 6. The vertex label, that is the name that is attached to the vertex, okay? So these are the names of those participants. I don't want anything, don't give me anything for that because it's a mess. The width of the edge, I want it to be this wide. The size of the head arrow, so each link, because it's directed, I'm getting head arrows, but I want it smaller because this is, yeah, very big. I want it 0.4, and you can tune this whatever you want. You just play around in your own computer, you'll see the differences. I want the edge being a little bit curved. Here you have it completely straight, and I think if it's curved, it's gonna be better. And the layout, I'm choosing this specific layout. What is a layout in a network? Do you know?
Does it have to do with the spacing, where things are spaced versus where how many nodes they have or edges they have?
Yeah, so basically it's telling you how the nodes are going to be spaced in your plot, okay? And there are many different algorithms, and each algorithm to decide how these nodes are going to be plotted in your graph have a different layout. So this layout nicely have a specific algorithm that is going to make the nodes be separated in a specific way. Okay, you can separate based on many things. There are many layouts, and depending how your graph looks like, depending how many nodes you have, depending on what you want to show, you might want to choose one algorithm, meaning one layout over another. At the end of this R script, I have this code here, and I'm going to change this one, and this one is GDS because we're going to work with that later, but right now I'm going to change into DS, okay, in two instances. One is here, the other one is here. I change it to GD, which is the network we're working on, and if I run all of this, it's going to give you something really nice.
If you
I was just gonna say, if you want at this point to incorporate in the network in a map that you can have each node in the position geographically, is that the layout?
That will be the layout. If so, you can have. But this code that I ran is giving you a lot of different, like is showing you your specific network in different types of layouts, okay, different algorithms. This is the same network, so depending on what you want, you might want to show this one, which is the one I chose, or you might want to show this one here, or this one, whatever what you want to show. If you want to map it on a map, I would recommend you to go with ggplot, which is what we did at the beginning the other day, and that was workshop number 3. Yeah, that is called map SNA with ggplot, because this is the way you're gonna plot it on a graph or on a map. Sorry, I mean there are 20 different ways of doing the same thing again, and every few months you have something new. But for me, so far, I will go with that. There is one of these layouts, which actually I don't know if it's this one. I don't not this one. Maybe it's this one. There is one of these layouts that is actually showing you the points plotted on geographical coordinates, but without a map underneath. Okay, but the only reason why this specific layout, which name I don't remember right now, can do it is because when we look at the network, we see that we have latitude and longitude for the vertex. Okay, if you don't have these, R doesn't know where to place those. Okay, so if I want to map it on a map, I will use ggplot as I explained before. Yeah, I'm wondering if there are other ways. I think, yeah, there are other ways for sure to plot it without a ggplot, because when I was working on my network in Georgia, I think, I plotted on a map without ggplot because ggplot was not that advanced. So I did it with iGraph. It's just like it's uglier. It's not as intuitive as ggplot. graph plot mapping, but you can still do it. And I do have some code for that I prepared for you, but then because of time I was thinking that maybe it's extra, but I can share with you as well. Yeah.
So the layout with MDS is basically on a map but without the base map?
I'm not sure if it's that one. Let's look at it.
I'm looking at it right now. It says multi-dimensional scaling of some distance matrix defined on the vertices of the graph.
Okay, let's look at it.
It's funny. So some of these I've just been looking them up, and they have they have like the Gmail address of the authors.
Yeah.
Email.
That's nice.
Yeah.
Yeah, no, so this is not the one I was referring to. Yeah, no, well, but ours is not multidimensional. We only have 2 dimensions, latitude, latitude and longitude, no? That's a 2-dimension. So multidimensional will have, if you're working with, with dimensions, with a PCA or MCA, multiple component analysis, but I don't know how you're going to plot that. I mean, I don't know. This one, yeah. There was another one which actually was telling you that it's taking, if you have latitude and longitude expressed as X and Y, it will automatically take it, but I don't remember which one it was. I mean, I can look it up if you want. But yeah, this piece of code here I think is really useful because it gives you an idea of different things. And then if you like one of those, just check out the layout and see what it's actually, what the algorithm is doing, because you might be interested in that or might not, depending on what you want to show. Okay, so I'm coming back to the first plot that we did. It was this one, the ugly one, and then when we ran this one, well, let's run both of them so we remember. This is the one that is not that nice, and then we change a few things and now it's nicer. Okay, and we see there are a few loops here. There's 1, 2, 3, maybe 4 loops there. Okay, it will be up to you if you want to see them or not. You see that now the edges have this little curvature. I said 0.1, so they're not straight lines, and to me that makes it look nicer.
So if you might be going over this, but if we want to just filter out the loops.
Yes, we're gonna go there just now because I always always work without loops, and also to do a lot of the more advanced things in statistically speaking with networks. What I found so far is like I need to remove the loops. I don't know if they have made something newer and now you can keep the loops, but the experience I have is we had to remove them. So I'm coming to that just now. We are going to simplify our network, and simplify the network can mean 2 things. One, we're going to remove the loops, and we're going to. And then another thing is like you can remove the multiple loops, the multiple edges. So for example, if between these 2 nodes here we have like that edge table and we have 3 different rows from A to B, that's a multiple edge. Okay, so instead of only having 1 transaction once during a year, let's say you have 3 during a year between those 2 different nodes. Okay, so you can set this as false, okay, or you can set it as true. I'm going to set it as true, but if I just do this, remove loops true and remove multiples true, I'm gonna lose the information about the amount of times that this node contacted this one. So I don't want to lose that. That's very important. So what I'm doing before simplifying my network, I am gonna assign a weight to each of the edges. So now I'm going to say each edge before simplifying my network is going to have a weight of 1. Okay, so one edge will have a weight of 1. If we have 3 edges here and each of them have a weight of 1, then if I collapse those edges and I say sum their weights, it's going to be 1 edge but with a weight of 3, meaning I see 1 line, but there were actually 3 transactions. Okay, so that is why I'm giving a weight to the edge. So this is the weight attribute, which is one of those special attributes. So you want to call it weight. You don't want to call it another way. Like name, that is created automatically, or color is one of those special attributes. So I create that. Now if I run GD, I see that we have a new edge attribute that is called weight. Perfect. And now I'm going to simplify. So for simplifying, I'm going to use this function, and I need to say iGraph package. So from the iGraph package, to semicolons or colons, use the function simplify. And I need to do this because I know I have a conflict with another package that I have downloaded, called, that also has a function that is called simplify. So I need to specify, take the simplify function, but from the package iGraph, okay? And then you write down the name of the network, and then you say remove loops, because I want to remove those loops, and then remove the multiple edges, okay? If I say remove multiple edges, I need to help R a little bit, because we are collapsing those edges, and I need to say how you're going to collapse them if you have edge attributes. And I'm going to explain it with this example we have here. We have for each transaction, let's look at, for each transaction, so for example, do we have anyone? This one here, okay? This is coming from this is the edge table, okay? And we have the origin and the destination is the same. Origin and destination is the same. But then the other edge attributes, the characteristics of each of those transfers are different. This one was done in September, this one was done in March. So what happens if I try to collapse these two? Okay, for the weight, I already say we're going to sum the weight. So we're going to have a weight of 2. But what about these other things? And it's a problem if I'm trying to collapse them and they are different. So we're going to have some limitations here. If I'm trying to collapse here, I cannot do much. Okay, so what I'm going to do with month, with the month variable, I'm going to ignore it. Okay, so I'm losing information here when I'm trying to collapse everything. I'm losing the month. For the number of pigs, I want you to sum them, because I want to know how many pigs in total during this year, let's think it's a year, there have been transferred from farm A to farm B. So sum them. For the longitude and the latitude, they're always going to be the same, because these are node attributes. So the farm A is always going to have the same latitude and longitude. So we were looking at these two examples. So the latitude and longitude for the origin, they're always the same. And for the destination, which are these two, they're always the same. So for that one, I'm going to say, okay, just choose the first one. Like, I don't care because they are the same. And I'm going to keep doing that with the rest of our variables. For example, the origin type, is it a farm or is it a slaughterhouse? So take the first one, because it's always the same. That is not changing. Okay? For the distance, the same distance between farm A and farm B, it's always going to be the same. So just keep the first one. Okay? And the weight that I talked about before, just sum it. Okay? So we actually only lost one variable, which is this one. So if you need that variable, we could think which other things we can do about that. There are ways around it, but right now, this is what we have. So now I'm going to simplify that network. And if I run this network, I see that we have 40 nodes. Perfect. We haven't removed any node. We are only messing around with edges. So 40 nodes, and now we have less edges. Okay? Which makes sense because we simplified it. If I run GD again, okay, this is the one that is not simplified, like graph directed. I can see I have the same number of nodes, 40, but I have more edges. Okay? We're going to be working with the simplified one from now on. Is this clear? Okay. So let's see. Let's plot exactly as before. This is the last one that we had. And now I'm going to plot it, but now I'm using GSD for my network. Everything else is the same. And we can now see that there are no loops. Okay? So okay, it seems we have simplified. Okay, let's see. I'm gonna change the visualization a little bit, and I'm going to add different colors based on the facility type. Okay, and that's okay. I don't remember which types of facilities we have, so I check first summary, nodes, premise types, and I have 3 different types. Okay, so I'm gonna create a vector that has 3 different colors, and these are the colors I want to use. Okay, if I call that vector, we can see that it's a vector with those 3 different colors. Again, in R you can call the color like this. This is a specified color, so if you tell R this, they already know this is the color orange. There are also numbers. The other day I was using numbers, like a combination of numbers that you can also use, but you can just Google color names in R, and then you will have a huge list. Now what I'm going to do, I'm going to create this new attribute for vector. We did something similar last time, and I'm going to assign this here. And what is this? These are those colors, those 3 colors that we specified, but it's going to assign those to each of the levels of this variable. Okay? Orange, sky blue, so you can see sky blue is the farm, because we have many, and then we have blue here, we have orange here. So I'm going to assign this vector as I'm going to assign that to the attribute color of the nodes, of the vertex. So now if I plot it again, I'm going to get the colors for each of those facility types. And if you see here, I haven't specified vertex color or anything, and that is because which you can do vertex color equal to this. Okay, this is what we saw yesterday as well. I can do that. I didn't run the set seeds, I need to run it. Okay, so it's the same. You can put it there, or you can just not write it down, because R already knows that color is for color of the vertex. So you can specify it, or you don't have to. Okay. Now I'm going to talk about centrality measures that we already saw yesterday, but this time the difference is like we're working with a directed network. Okay, so we're going to calculate the in degree. So I write degree of my network, and then use this as nodes, and then the mode is in. If you want it for out degree, the mode is out. And I say, yeah, don't look at the loops, although we don't have any loops because this is simplified. So I run it, and these are the in degrees for each of my nodes. Okay, so now I'm going to take that in degree vector, and I'm going to assign it to a node characteristic, node attribute for the nodes that is going to be called indig. Okay, so now if you look at GDS, you're going to see a new node attribute, or maybe 2 because we have the color here. We have the color, it's a new one that we didn't have at the beginning, and now we have in degree as well. Okay, so this is a way you can double check if it was assigned properly or not. So now let's plot it, and now I'm adding this vertex size. Before we had equal to 6, and now I want the vertex size to be equal to the in degree of each of those nodes. So now the nodes that have the higher in degree will seem larger in the plot. And I'm also adding a title of my graph that is called in degree. Okay, so I run it, and this is what I get. We're not very surprised because we saw it also when we were mapping it on Thailand. We also had kind of the same thing. So a way to minimize it will be what I'm doing here is exactly the same code as above, but I'm changing this. I'm taking the nodes, okay, the size equal to the in degree of the nodes, but I'm doing a log of that, okay, and because these numbers are really small, I'm multiplying that times 5. Okay, so the sizes are gonna be this. They are different than the real in degree values, but they're all the same. They have it's just a transformation that I did, so it's still really valid, and it looks a little bit better now. Okay, these are ways you can change it. If you want to see the name of the biggest one, like which one is this one, is huge, but I don't know which name, which is the name of that farm. So we can do, I'm creating a new object here that is called larger label, largest. Oh well. Largest label. Largest label. And I say, okay, I'm going to use the function if else that we already know, but I'm using it again because I'm sure we have forgotten. And I say, okay, if the in degree of a specific node, whenever you are looking at each node, is equal to the maximum of the in degrees, and what is this? 39. So if the in degree of that specific node is 39, which is the largest of our nodes regarding in degree, give me the name of that node. Otherwise, don't give me anything. Okay, so basically what I'm doing here is like, give me the name of the largest in degree node, the node with the largest in degree. Okay, so I create that one. And then I say, okay, now I'm going to plot it, same as before. And what I'm changing is the vertex label. Okay, first, before I had vertex label NA, I didn't want any of them. But now I want the largest label. Okay, so if I run this, but I'm going to run this only. So let's see what that is.
JSON.
This is what we have. Okay, JSON, and then nothing for the others. So if I run this code, we see, oh, JSON is there, but I cannot see it that well because of the colors. Okay, so what do you think I can do to change the color of that vertex? So that will be, I want to change the label of, the color of the label of that vertex. So what do you think I can do?
Color of the label.
The color of the label. Perfect. So I'm going to go with, let's see if this works. Vertex label dot color. Okay, and I'm gonna say give me yellow. Okay, and now I put a comma here at the end. Okay, so what I just did, I added this line here, this attribute argument, sorry. I said give me yellow, and then I added a comma so the code can keep reading. So if I run that, okay, it's better now. Okay, maybe not the best, but we can keep playing with it. But
Wait.
I did what I did. So what is the error that you get? Let's try to understand.
No, it's just a notation. So larger label.
So I added this little comma here. Sometimes we can forget doing those things because we add. Yeah.
And how do I know that it's going to that one only? Oh,
Because I chose it here.
okay.
I say, give me the name, but only of the one that has the largest in degree, like max. If you want minimum, you could say, let's do it here. Minimum, and probably we'll find more than one. Okay, so we have two that have the minimum. So now if I run this one, this I will change the name. I would say minimum, and I will put here, this here, and then we will have the minimum, the nodes with the minimum in degree. And you can have both minimum and maximum, things like that. You can change it. Or if you are looking at a specific one, you can say, give me the name of this specific one. So you can change. This is like all the things that you can modify to finally get a graph, which is what you want to show. Okay, so now I'm going to do the normalized in degree. Okay, and normalize, if you look at degree, is normalizing. This is good because you can compare different degrees or in degrees with different graphs that you have, and because it's normalized, you can compare it. If it's normalized, you wouldn't be able to compare it. Okay, so the way the degree function uses normalize, what it's doing is dividing the results by n-1. Okay, maybe you want to normalize in a different way, and if you want to have the, so we have the in degree, this is our in degree, but maybe you want to do the in degree minus the mean of the in degree, and then all these you want to divide it by the standard deviation of in degree. This could be another way of normalizing, for example. Okay, so depending what you want, but the function degree, if you ask the function degree to normalize it, where am I? Here, it's gonna normalize it in this way. So this is why it's important to look at the documentation to actually know what R is doing, because maybe you're fine with it, but maybe you want to do it in a different way. Okay, and the good thing with R is, like, most of the times you can do it in a different way, but you need to know what R is doing to be able to assess if that's what you want or not. So I'm happy with this type of normalization. I run it. These are the numbers of the in degree normalized. So again, and I assign it as a vertex attribute, okay? And now I'm gonna plot it, but the vertex size, now I'm changing it to the in degree normalized. And because it's so small, and because I already ran this without this 50, I decided I'm gonna multiply it by 50, okay? To be able to see it a little bit better. Okay, and this is what we have. You can decide to multiply by less, you can do the square root or whatever you want. Those are transformations. Another way of calculating the in degree could be calculating the weighted in degree. So the weighted in degree will be similar as the in degree, but we will be checking how many edges, how many transactions happen. So here, remember the weight attribute of the edge, the edge attribute that was weights. Wait, there. Okay, this is the number of the transactions that happen between the different nodes. So what I'm doing here, I am weighting it by the number of transactions. So what I get is this one here. If you compare this with the in degree, you can see that it's a bit different, okay? Some of them are the same. If the weight is 1, it will be the same, but if the weight is something different than 1, it will change a little bit. You can also weight them by the number of peaks, for example, okay? So I think we had it number of peak, I don't know if like this or with one S, let's see. Yeah, no, because it's the same. Yeah, there it is, okay? If we weight it by number of peaks that were carried out in the sum of all the transactions, then I will be weighting it by the number of peaks, okay? By default, if you don't say, if you skip this argument, because our node is a weighted node, and you can see that by looking at the node, now you see this W? Remember at the beginning we didn't have it, but now we have it because we assigned a weight here. And I told you this is a special attribute of edges that are recognized as, okay, now we have a weighted network. And that's why now we have a W there, okay? So, because it knows it's a special attribute, it's the same thing with that color thing. You can put it or you cannot, or you can skip it. So, if I run here, if I run this line of code without this, it doesn't matter because that is actually the default. Okay, well, the weight, if I have this weight. Weight here will be the default. So I can run it like this, or I can skip this part, and I get exactly the same thing. Okay, but I left it there, oopsie, because I like seeing it, and also I want to be able to change it. Okay, so you can decide whatever you want. Okay, so I created that weighted in degree, and you saw the difference with the normal one. Now I assign it. Well, I put here big, so I'm gonna put weight again. But you can put whatever you want. I'm gonna assign it to a node attribute, and then I run it. I change the name of my network, and this is the weighted in degree. Okay, so now you have this exercise. This is for you, and we can have a break. Okay, calculate the out degree and then plot it. So it's very similar to the in degree. Okay, and I'm just asking you to calculate the simple out degree, and then I want you to calculate the weighted out degree. So I'll give you 5 minutes, and in those 5 minutes you can do this and have a short break and then come back. So let's see the answer. We have it here. So we calculate the out degree. So it's basically the same degree, but the mode is gonna be out. Okay. we assign it to vertex attribute, and then we plot it. What I did the log of that out degree, and then I multiplied it by 5. You can do whatever you want. You can do that. You can do just that, and then you will get something like this. Okay, so you can modify it as you want. Then for calculating the weighted out degree, I change the function and now I use strength. Okay, the rest of it is exactly the same. I assign it, and then you will plot it like this. So I just copy paste, and then I take this one for the size, run it, and you can decide how to modify it. For example, I divide it by 2. Let's see what will happen. Okay, so it's up to you. Now for betweenness centrality, very similar as what we just did, but the function that I'm using now is betweenness, and I'm going to normalize it. Again, here for betweenness centrality, if you have a weighted network, it's gonna take this attribute of weighted and it's gonna use the weights of your network by default. So if you don't have them, you will have to change them. Okay, so this is a normalized and weighted betweenness centrality. I assign it to my node attribute. I put it in the size here, and here I've done this transformation. You can do whichever transformation you desire. Okay, now another exercise is closeness centrality. Okay, it's going to be very, very similar to what we've done now. And the function we're going to be using, you can see it in the undirected network that we had before. Okay, so if you go up here, somewhere here, you will find the function, and then you can try to run it, assign the value to the vertex as a vertex attribute, and then plot it. Now, okay, so closeness centrality. Any questions with it? Okay, so we have closeness, normalize, and is it weighted or is not weighted? If I ask to have this, is that weighted closeness or normal weight closeness?
Normalized closeness?
It's normalized, okay, and is it weighted or not?
It's weighted.
It's weighted. Why?
Because you say normalized weighted closeness in the title.
Yeah, because I say that. That is true.
Because it's already in your file.
In the
You
function.
created
Yeah.
before, and just dragging it.
I created before. I don't think I created closeness yet.
Oh no, the weight.
Uh-huh. The weight, exactly. So my network is a weighted network. We can look at it here. Okay, it's a weighted network because we did it. We created it. And this function, if you don't say anything, by default, if the network is weighted, it's gonna take the weight attribute for the weight argument. Okay, sorry, this argument. So yes, it is weighted. If you don't want it weighted, you will have to modify it.
Can
Okay.
Would you say no? Is that
I would say NA. I don't know. Let's see. I don't know how that will work. So if I run this, those are the values, and I will explain this now. So let's say I will say NA or null. Let's see. No, that didn't work. So let's see NA. No, so it seems we cannot change it to 0. Or what about?
Can you say false?
Can I say false? Let's see. No.
No.
Okay. So no, we cannot. What you can do is you can change it to something else. For example, number of peaks instead of the weight of the edge, which is the number of transactions. Like something continuous. It will have to be a continuous variable. Oh? Okay, there it is. Okay, so we change it, instead of being the H attribute weight, now it's the H attribute this. Okay. I mean, what you could do, yeah, you could change, but why would you do that? You could create this. So we have this one, no? Yeah, we have that one, and you can say, okay, give it a 1 right now. So that will make all of this 1, which is as if it was not weighted, but I don't want to do that because then I mess up with my network. Okay, so when I run the code that I gave you, this one here, it gave me this problem. Okay, it says is closeness is not well defined. So I'm giving it to you, but don't trust it because it's not well defined for disconnected graphs, and it seems that our graph is disconnected. We'll see what that means now. Okay, still I'm gonna plot it just for the fun of it. Okay, very similar things, but here in the size I'm doing weightness, closeness, weighted closeness, and you have it here. Okay, actually this should be normalized weighted. Okay, now we're gonna go with chunk 2. That's the end of your exercises. This is gonna be just, so we finished chunk 1, and this is a little summary of what we saw yesterday. The importance of the node, which node is more important, depend on what we're looking for, which question we're asking. Okay, and then I'm going to talk about these 5 number summary. So there are 5 characteristics of a network that are really useful in defining how your network looks like. Okay, there are many others, there are so many, but these 5 are quite generalized, and a lot of people will understand what type of network you have if you tell them these characteristics, besides saying if it's directed or not and all those things that we've already seen. So one is going to be the size, which is how large the network is. The other one's density, how densely connected. Components, whether the network is made up for one or more distinct groups, different groups. Diameter, how compact it is. And clustering coefficient, if we have clusters in a network or not. So we're going to go one by one through those. So for the size, most people consider that the size of a network is the number of nodes. Some people think that the size is the number of edges, so that's a bit confusing, but most of the time I've seen it as the number of nodes. Okay. Then the density, it's a ratio, and it's the ratio of the number of edges that you have in your real network. For example, here, the number of edges, the lines that you have there, versus the number of possible edges. That will be the number of edges if all these nodes will be connected. Okay, so that ratio will be the density, and it goes from 0 to 1. Components are different subgroups that we have in a network. For example, all these, we have all the networks are connected somehow, directly or indirectly. You can reach this node, for any of the other networks. Maybe you have to do a lot of different steps, but you can reach it. If you cannot, because they are disconnected, then you have different components. Okay? And this is what you have problems when you have a network like this that is disconnected. You cannot calculate some of the measures that we have been calculating because then the definition doesn't apply well. Okay, and I think that by default it will calculate it from the largest component. I think that's the case. I might need to check. So those 3 are the 3 that we just saw. Then we have the diameter. The diameter is the maximal shortest path. So it's the longest of the shortest paths. Okay? Across all pairs of nodes. So that's the diameter. It gives you an idea on how it's another of these components that it tells you how many steps your shorter path has. Okay, the largest one, sorry, maximal shortest path. So what is the from those shorter paths that we saw yesterday, which one is the largest? Okay, so that gives you an idea on how connected that network is. And then we have the clustering coefficient, which basically is like, are there clusters in your network or not? It goes from 0 to 1, and a synonym of that is transitivity. And the way it's measuring clustering, because there are different ways of measuring clustering, it's a proportion of of triangles, and closed triangles and open triangles. If we have these are nodes and the lines are edges, this is a closed triangle, okay, and these will be open triangles. So this gives you an idea. If you have a lot of these, there is a clustering among those nodes, and if you have this here, there's no cluster at all. So it's measuring like the differences between the triangles that you have, the closed one, and the ones that are not triangles but could have been triangles if there was a cluster there. And that is giving you this value from 0 to 1. Okay?
So
Question.
Do you think that this clustering coefficient could be useful when you're trying to target locations, for example, for a collaborative or something? You want to see which ones are clustered,
Yeah.
which facilities, and
Yeah, definitely.
that would be kind of as an initial approach, and then you decide, okay, this seems to be.
Yeah, this cluster coefficient it goes from 0 to 1, and I think it can be local, meaning for each node, or it can be general for the whole network. What you are talking about, I think, is more a community, and we will see it later. There are different what we call community algorithms, because again, like the same with clustering, saying there is a community here, which is basically there is a cluster here that is formed by these different nodes that are trading more. That decision of being a cluster or not can be made in different ways. So there are different algorithms that will give you an output of different communities, or community, in the sense that these are nodes that are trading a lot with each other. So in that sense of seeing, like in a real case of these different hospital facilities, to see if there are clusters, like groups of facilities that are trading more amongst each other than with the average rest of the facilities that we see, I will be looking for communities. Okay, and we're gonna see that's the last piece of code of today is communities. Okay, so I'll give you some examples. Then it's difficult sometimes to choose which algorithm is the best for your communities, and this is another area in the network analysis that is been growing. At the beginning, there were algorithms, but they will only address undirected networks. Now there are some that can address directed networks. Okay, so it's also a growing field, and this is like really clever people who are working on that. And then we just plot it, we just plug it in our function, and I'll show you one of those. So going back to the code, I'm gonna run really quickly those 5 characteristics of networks. So to look at the size, this function here is gonna give us the number of nodes that we have, and this one here the number of edges. Okay, you know that you can also get the same thing from here. Okay, number of nodes and number of edges. And this is another way of doing it. Then we have density. We can do it with loops and without loops. Okay, which now actually it's very false. Let me do this one here. Yeah, you see it changes because we have, and I'm actually surprised that this is simplified, doesn't have loops. I was expecting this to be exactly the same. Yeah, the difference is not that big, but it is different. I don't know why. That I will have to explore, because it's simplified, so we should not have any loops there. So I don't know why this is different. But and this one here, I ran the same thing, but with the graph that was not simplified. Okay, so we still have loops there. So the equivalent will be edge density. This is another term that they give it. Then we have the components. These are the different components, and we don't have any big separation. Okay, so we have one component that has 40 nodes, and this is the membership, the component each node belongs to. If we had 2 different ones, we will see, I don't know, if Jacob is actually a bit different. This is the slaughterhouse. I would have expected that we will see 2 components. Jacob will be different than the others, and then here I will have 1 and 2 number of, so I will have, a 2 for number of components. The cluster size for the first one, I don't know, 39, and then the second one, Jason, will be another one. But this algorithm hasn't seen that.
So what does the no mean?
No is the number of components that we have. And right now we have 1 because,
So
yeah,
everything's connected.
everything's connected. Yeah, looks like it. Okay. Then we have diameter. Okay. Diameter of 6. This means that it takes 6 steps to connect the two nodes that are situated the farthest apart in this network. Okay, so the diameter is that maximum shortest length. Okay, so from the shortest path from the shortest path, the maximum is, yeah. And this is why I need to read it, because I always, it's a mess. Yeah. But yeah, I mean, when you're gonna describe this in your manuscript or to your boss, you will give them this explanation, and then I always have time to look at the explanation and make sense of it within my example. So yeah, then it makes sense. And transitivity, which is the clustering coefficient, yeah, you can do it global, which is for the whole network, okay, and you can do it local, which is for each of the nodes. This is the clustering coefficient, like how much is really connected with other ones near them. And this is the triangle, the closed and the open triangle. If you try to do the exercise with a small network, you can see it, but it's complicated, because again, there are triangles that you didn't see, but there are exercises online with small networks that you can actually visualize it, and they're useful. Question?
Sorry, what's the difference between local and global?
Local is for each, this is the transitivity or the cluster coefficient for each of the networks. So you see this one here, which is, I think it's the slaughterhouse, has a high clustering coefficient, because it's really like everyone is sending to him, so it's really there in the middle. This one here, I don't know which one he is, but the clustering coefficient of that specific node is pretty low. And the global is for the whole network. In general, there is this, so this you can compare with others. Okay? So now for community algorithms, I brought one here, which is the wall trap community algorithm. There are many others, okay? So I use this function. Okay, and this algorithm says that there are two different groups, okay? One is this, the other one is that one. Okay, two, or no, actually, there are more. Omitted several groups, so there are more. It's only showing me two. So I'm going to say, okay, what is this wall trap cluster algorithm? It's a community object, okay? This is a different object we've never seen before. It's very specific, and it's a community object. Modularity. Oh, I'm sorry, I don't remember modularity, what it means. I thought I had it here. I don't remember. I'll look it up and let you know, because I don't want to make it up, because I'll get confused. And here you can see, okay, there are at least three different classes according to this algorithm. So this number denotes or explains to which group this node pertains. So this one is from group 1, this one belongs to group 3, this one belongs to group 2, but okay, I want to see it visually. I'm going to understand much better once I plot it. So if I plot it, we get this. Okay, and I think this is what you were referring to, Moniz? Yes? Yeah. So these nodes here, they have more trained within themselves. This one here, they trade a lot within themselves, and this one here. If you see the black edges, so this is automatic, that if the transfer has happened within the community, the edge is depicted in black color. If the trade is happening between communities, it's going to be in red. Okay, so you have an idea of what's happening there.
And again, this is not considering time, right?
This is not considering time, exactly. So if here I have a 1 year, yeah. So if you want to consider time, there will be other ways that we could do. Either you chop it per month, you create a different network per month, or there are some dynamic network things that can allocate time.
Yeah. I'm just thinking if we're thinking of transfers, or whatever or maybe outbreaks or disease.
Yeah, exactly. You want to look at time. I totally agree. Yeah. And there are ways of doing it. Yeah. Okay. So yeah, we can do a dendrogram. Our plot is a bit. The thing with this is, like, as soon as you get a little bit of a big plot, it's not useful. And this is the different layouts we already talked about that I showed you at the beginning. So with that, I'm done with the code. I'm not done with everything yet, but I'm done with the code. And then if I go back to the slides, we did chunk 2, okay? And then this is something that we need to think about. Yeah, when we have a big network, it's very difficult to actually visualize it in the way we have been visualizing, because you'll get something like this, which is pretty. I mean, you can see there's one community here, another one here, and this one here, which is really intertwined with the green one. Okay, I don't know if this one's different from this one, maybe. This is not mine. But yeah, I mean, it's pretty, but you cannot see that much. So how do we deal with this? There are different ways. You can do subsets. You can do subsets of nodes, like maybe you want to look only at one county. Or by facility type, maybe we want to look only at the acute care hospitals. Or we can do an egocentric network, like if you are specifically interested in one of those facilities, like remember the example of the slaughterhouse, you can simply plot those that trade that specific facility had, either in like sending out or receiving. So you can change those things to try to make the visualization of your plot a bit more understandable for the human eye. You can also group by county or facility type. This is something that I did yesterday. I did an arc plot. I actually might have it here, but it's still under construction. I mean, I'll show you later. But I think that's something that you wanted to do, Sam. So yesterday I worked on that. It can be improved, but the idea is there. I mean, it just like doesn't look super pretty. I still have to change some visual parameters, but it's there. Or you can try other software options, which I was very excited. There's this Gephi one that looks really nice, but still, it's a huge network, and you're gonna get something like this. I mean, I think this was done with Gephi. I don't think this is R, but I'm not sure. We don't have access to Gephi here because it's like protection security thing. So I want to ask for a permission to use it, but I need Erin's signature. So, and also it depends if she wants me to work on that or not. So we'll see. But I mean, at the end, bottom line, you can chop your network into pieces and try to visualize special portions of it. That if you have a huge network, you're gonna get something like this. Yeah, you can change the colors. You can, but it's very difficult to see. And imagine if you are plotting this in a map, on a map. If there are a lot of lines, there are gonna be a lot of lines. So that's the difficulty of showing everything. You can show everything, just like look how everything is very interconnected. That's perfect. If that's your aim, it's great. This type of plot will be great for that. But then if you want to go more into detail, then you need to do these subsets or grouping. Okay. So some references here. This guy, this is the Thomas website that I was telling you about, the one who's working on the gggraph. Amazing. You can spend a lot of time with that website. It's very nice. It's still short, it's still small, but he's working on it. So that's all. I'm going to stop this, and I can show you the arc map if you